Perfect. Okay. Morning, everyone, again. Those who are watching us offline as well as online. Couple reminders. Tomorrow, let me put it down. Don't forget, we have the scheduled meeting with Professor Thomas Strummer. Same time, same place, same Zoom link. This is an exclusive meeting for our group, so please come. If you don't come, you need to watch it online. You may do that, but I really want to encourage you to come online because the person is coming to talk to us. So please do that. He's one of the experts in modern applied mathematics and data science, computational harmonic analysis, and is involved together with me in a big project in building private and synthetic data. So don't miss that opportunity. He's also connected to companies in the Silicon Valley. So please do that. And this is our lecture 28 in high-dimensional probability and applications.
Sorry, you are not sharing screen.
Yeah. Sharing screen. Thank you. How do I do that? Thank you so much. Share content. Okay, now much better. Here we go. It's lecture 28 in high-dimensional probability and applications to data science. And what we finished a big block on random matrices. What will happen next is that maybe like 4, maybe 5 lectures on matrix concentration. This is a newer area in probability theory and data science, starting maybe 2008, 2010, 11, 12, something like that. Then we will do, I don't know how many classes on VC theory in applications to machine learning, and matrix concentration applications to community detection in networks, and to mixture modeling. And VC theory to machine learning. And then if time allows, we will do a little bit of maybe 2 classes on differential privacy. And that will take us into the beginning of December already. So that's a big plan. Okay. Any questions before we go on with the matrix concentration? We start to build that. Good. Okay, good. So what's the big idea that we're going to explore now? It's kind of a dream. Can we work with matrices as we usually work with numbers? Just pretend that they're numbers. Like you can multiply matrices, you can add matrices and divide. Well, you just multiply by the inverse. You can do a lot of things. You can square matrices and stuff like that. But then can we just pretend that they're numbers, work with them, and obtain results in a much simpler way than by looking at them as real matrices? For example, the covariance matrix, a sample covariance matrix, 1 over n sum xi transpose. You've seen it a lot of times. This is a sum of independent random matrices. Rank 1 matrices, right? They're independent and rank independent, identically distributed, xi transpose. So it looks like the sum of independent random variables. So if we pretend that these are independent random variables, then we know a lot of tools for them, such as central limit theorem, law of large numbers, more sophisticated tools such as Chernoff or Höfning on Bernstein's inequalities. Can all of this be just extended to matrices? If so, then we would have a very nice, very convenient tool to work with. And that is what we would like to explore. Trying to work with matrices as with numbers. It's a very simple idea, and sometimes it's possible, and we'll identify the roadblocks and try to remove them as they arise. So this is generally called functional calculus, this idea that you can work with matrices or with operators as numbers. So we'll, just for the sake of simplicity, we will always work with symmetric D by D matrices. Always. We know how to add them. We know how to multiply them, add and subtract, right? So adding, subtract, that's fine. So in this respect, they do look like numbers. We know how to multiply them. Also, like can pretend that they are numbers. We can divide by multiplying by the inverse, maybe. Just like numbers, there is a zero. It's a zero matrix. It really, in all respects, it looks like a zero scalar. There is a unit there, so the number 1 gets replaced by the identity matrix. So there is an analog of 0, and there is an analog of 1. There is analog of multiplication and division and everything else. There may be an analog of the absolute value, which is the norm. Let's say the operator norm. Operator norm. It's kind of, I don't know, philosophically, this looks like an absolute value of, or proxy for an absolute value for a number. Okay, so this is all clear, and we can take some functions of matrices. We already know how to do that for example, I don't know, inverse. That's a function of a matrix, or square. It's easier to write this in terms of the spectral decomposition. So if we express the matrix in terms of the spectral decomposition like this, then we know how to square the matrix. To square the matrix, this is already in the diagonal form. So squaring the matrix would amount to just squaring the eigenvalues, like that. Yep, that's how we square the matrix. Because similarly, we know how to take the inverse in this form. Just take 1 over lambda I transpose. Okay, so we know these 2 functions already. We can build more complicated functions this way, such as this one, for example. Any quadratic polynomial of a matrix, then again in this form, in the spectral decomposition form, it would just amount to make the corresponding transformation of the eigenvalues, like that. Agreed? Yeah, very simple. Okay. And similarly, for any polynomial P, we can build the polynomial of a matrix in the same idea. P of lambda I, ui transpose. So we know how to build polynomial of matrices. And then it becomes only natural to define any function of a matrix just by looking at this expression and generalizing it. So if you want to define any function here, just apply that function to eigenvalues. That'll be our definition. And that's called functional calculus. So if f is an arbitrary function, and A is a d by d symmetric matrix, here is what is f of A, how we define the function of a matrix. We express A in the spectral form, like this. And define f of A as just by applying the transformation to the eigenvalues only. Just leave the eigenvectors alone and just do it this way. Good, agreed. Do you guys, some of you may know it already, maybe, I don't know, functional calculus. Okay, so this is how you build any function of a matrix. And the big idea is to get matrices, to work with matrices with numbers, and we can take any functions on numbers. Now we can take any functions of matrices. Okay, great. As an example, we can exponentiate a matrix, e to the a. E to the a. Let's see. E to the a, that would be, and I'm claiming actually that we can write the Taylor expansion in matrices. So remember e to the x, let's see, e to the little a, what would it be? It's 1 plus a square over 2 factorial plus a3 over cube over 3 factorial, right? So this is a Taylor expansion for the exponential. So I'm claiming that this is the same holds for matrices. E to the a is 1, which is identity now, plus a, plus a squared, which is just a matrix squared, divided by 2 factorial, plus a cubed divided by 3 factorial, and so on and so forth. So we have Taylor expansion. Why? Let's quickly check it. Let's quickly prove it. So e to the a, how do we define it? We take the spectral decomposition and apply the transformation only to the eigenvalues. So e to the lambda I, ui transpose. Yeah. Then what do? Then we write the Taylor expansion for e to the lambda I. This is a usual scalar Taylor expansion. Lambda is a number, so this becomes 1 plus lambda I plus lambda I squared over 2 factorial, and so on and so forth. And then we break the sum into the series, right? So the sum will be sum of I1 to D1 times ui transpose plus the second term was lambda I ui transpose. The third term was lambda I square over 2 factorial ui transpose, and so on and so forth. Yep. And well, obviously this is, so the second term is obviously a, that's how we defined it. The first term is identity, and that is because ui formed the eigenbasis, the orthogonal basis, so that's identity. The third term is what we defined a squared over 2 factorial to be, and so on and so forth. And so we're done. I'll just prove this beautiful expression for matrix exponential. Good. In the same way, we could do this for any real analytic function, any function that is expressible as a Taylor series, right? This argument was not really special to exponential. We could do any function. which gives us an alternative definition of what a function of a matrix could be. It could be the following. If the function is nice, if the function is reanalytic, write its Taylor expansion, and then replace the numbers there by the matrix. And that's, then you get an explicit definition of a function of a matrix, alternative equivalent definition. But for most part, we will work with this definition. It's more general. So that again, how do you take the function of a matrix? You just apply that function to eigenvalues alone and leave eigenvectors out. Any questions? We're good? Okay, cool. So we defined functions of matrices, functional calculus. Perfect. What else? What would be the dream? What else do numbers have, and what else we would like matrices to have? So we know how to multiply, we know how to add, subtract, divide. We know now how to take any functions on matrices. And then there is one thing that real numbers have, and the matrices kind of don't, is the order. I can say that 3 is less than 5. But I can't really say yet that this matrix A is less than this matrix B. So we need to define an order on matrices. That order is called, the canonical order is called Loewner order on the set of all D by D symmetric matrices. And it's very simple, really. It kind of recycles the notion of positive semi-definiteness. We know what the matrix positive semi-definite is. So we can say that, this matrix is define this order, that this positive semi-definite matrices are greater than 0. Once we know how to define a matrix greater than 0, we can compare matrices. A is greater than B if A minus B is greater than 0, which means that A minus B is positive semi-definite. So that's it. Okay, very simple order. Let's write this down. So this order recycles the notion of positive semi-definiteness. A is positive semi-definite if and only if, and this is a definition. The quadratic form U transpose AU is a positive number for any vector U. So that's a definition of positive semi-definite. Equivalently, A is positive semi-definite symmetric matrix is if and only if all of its eigenvalues are non-negative. And then Loewner order becomes a trivial idea. Just declare that a matrix is non-negative, and let's I don't know, that would be wrong to say. Let's just write something like curve 0. Invent some other notation for this order. So you say that A is greater than 0 in Loewner order if A is positive semi-definite. And if we have two matrices, then we say that A is greater than B, or equivalently, B is less than or equal to A, if A minus B is positive in this order. Which, according to this definition, means that the quadratic form generated by A, U transpose AU, is always greater than the corresponding quadratic form generated by B. Good. Any questions? Loewner order clear? Yeah, it's very clear idea. Perfect. It comes with all the perks of the natural order, but we have to be careful here because this is a partial order. And not a total order. By this, I mean that there are matrices that are incomparable, that you can't say which one is larger. For reals, the usual order on the numbers, on real numbers, is a total order. You can always say that, A is less than or equal to B, or B is less than or equal to A. But for matrices, it's not exactly true, not always true. For example, if you have a matrix like this, 1, -1, let's say. For this matrix, it's not true that A is positive semi-definite because it has a -1 eigenvalue. Right? And it's also not true that A is less than 0, so -A is positive semi-definite. Also not true because there will be another eigenvalue that's negative. So this matrix is incomparable. These two matrices, A and 0, are incomparable. You can't really say which one is larger. And that's okay. And for complex numbers, for example, complex numbers, we have a partial order maybe, but not a total order if we want to. That's fine. Good. Okay, so far so good. Now, let me ask you guys. So far, everything works very smoothly. Our kind of dream, if I dream about working with matrices as with numbers, I can just do pretty much anything. I can add, multiply, I have 0, I have identity, I1, I have absolute value. By the way, if I have absolute value, then I have the distance. A minus B would be a nice distance between matrices as distance between numbers or vectors. And then we can take any functions of matrices, and we can write Taylor's expansions if we like. And we can compare matrices as we compare numbers. So everything kind of works very, very smoothly so far. But it's too good to be true, right? There must be something there. There must be some catch, right? You can't really push this too far. Matrices are really different objects, and so tell me, guys, what is the one kind of an elephant in the room, the one big roadblock, something where matrices really behave differently from numbers, something that real numbers have, and the matrices fundamentally fail. Some property. What is this?
Commutation.
Commutation, exactly, Katerina. Yes. So numbers commute, right? 3 times 5 equals 5 times 3. We know that. And matrices don't. Matrices don't commute. Not all of them, but some don't commute. And that is a big thing that makes many arguments invalid, because many of them are implicitly dependent on the commutative order. So yeah, so the warning here, and that will be our main nemesis, is that matrix multiplication is not commutative. XY is not the same as YX, generally. As a result, some very basic facts, very basic arguments do not transfer from numbers to matrices. So this is our unhappy face. But maybe it's actually should be a little bit a happy face, because that means that matrices are really different objects. They're richer than numbers, and we'll see that. very simple facts can fail. For example, X can be positive semi-definite, Y could be positive semi-definite, but X times Y may not be positive semi-definite. So this is not always true. Well, actually, let me tell you this. Okay, let me tell you something. So this is true for commuting matrices. X, Y. Do it yourself. It is true for commuting matrices because commuting matrices are simultaneously diagonalizable. What does that mean? It means that they are diagonalizable by the same orthogonal transformation, which means that I can write their spectral decompositions with the same eigenvectors. And so that if you multiply these matrices, you'll see it very quickly. But in general, for non-commuting matrices, that may not be true. In fact, X times Y, the product may not even be symmetric. Oh my goodness. So this is not only non-commutative, but we decided that we're staying within D by D symmetric matrices, and the product not only doesn't commute, but it actually takes us out of the set immediately. So X times Y may not be even symmetric. So that's not good, definitely. What's the way around? Well, here's a life hack. A better way to multiply matrices is to multiply on both sides. If X is greater than Y, and A is any matrix, D by D matrix, not even symmetric, then here's a good way, a valid way to multiply. A transpose XA is greater than A transpose YA. So if you multiply on both sides, we're fine. Why? Let's check. Well, first of all, without loss of generality, we can assume that Y is 0. Why is that? We can move the right side to the left side, and you'll have X minus Y inside. So declare X minus Y to be the new matrix. So let Y be 0. Then I want to check that A transpose XA is greater than 0. What does this mean? I need to hit it with U on each side and check whether this is greater than 0. What is this? This is, I think this is AU transpose X AU. And yes, it's greater than 0. Because X is positive semi-definite, and this is a definition of positive semi-definite, hidden on both sides by some vector, like V transpose XV. Okay, so we defined a lot of things, including the functions and order on the matrices. But the one thing is fundamentally flawed, which is product is not commutative. It's even can take us out of symmetric matrices. And so we have to be super careful there. We, instead of doing this careless thing, which would not be true for symmetric matrices, we say, okay, there may be different life hacks. One of them is to multiply on both sides. That will be okay. Any questions? Room one? Good. Okay, perfect. Okay, so we defined the order, and an important thing is to understand how order affects the eigenvalues, because that is our main will be our main object of study, eigenvalues of matrices. So eigenvalues and the Loewner order. Let me recall something. Loewner order is the order defined by positive semi-definiteness. We say that A is greater than 0 if A is positive semi-definite, which means that all eigenvalues are positive. So there is an intrinsic link already. A is greater than 0, if and only if all eigenvalues of A are greater than 0. That's Loewner order. Perfect. What about two matrices? If X is less than Y, will it be true that eigenvalues of X are smaller than eigenvalues of Y? It's not immediate, because as you know, eigenvalues are not linear. Eigenvalues of X minus Y are not the same as eigenvalues of X minus eigenvalues of Y. So I cannot just rely on that. But we can rely on something else. We can rely on the variational characterization of eigenvalues. Let's recall this from several lectures ago. It's called Courant-Fisher min-max theorem, which gives us a geometric meaning of eigenvalues, actually. So lambda I of a matrix of X. The lambda 1, the first eigenvalue. Remember what first eigenvalue? Is a maximizer of it's a maximum of this quadratic form. Right? The top eigenvalue of the operator norm is obtained by maximization of this quadratic form. Now the second eigenvalue, remember what to do? The second eigenvalue, we take the residual. So we remove the first eigenvector, look at the hyperplane, the span of the rest, and again maximize the quadratic form, and then we iterate. So that's what I'm going to write now. So this is maximum, I think something like this, maximum over the subspaces E of dimension I, minimum over all unit vectors in E. Max-min theorem. The point is that if X is less, let's say, if X is in this semi-definite order is less than Y, then the quadratic form is less than the corresponding quadratic form for Y. And this is the eigenvalue of Y. Max, min. So it does hold that the eigenvalues also compare. So what we proved, proposition, let's call it eigenvalue monotonicity. That the eigenvalues are monotone in Loewner order. So if X is less than or equal to Y, then all eigenvalues of X are less than or equal to all eigenvalues of Y. Good. By the way, the other way around doesn't hold. It's only one way implication, and we will only this way is true, and this way is not true, and that will be in the homework to check that. Check that. Okay, good. If X is less than Y, then eigenvalues are less. Now what we can do, we can sum now. We can add up all the eigenvalues, and we get what? What is the sum of the eigenvalues?
Trace matrix.
Exactly. Yes, that's a trace. So we automatically know that if x is less than y, then the trace of x is less than trace of y. In fact, before we sum them up, we can apply any function. And we will get this thing, corollary, trace monotonicity. The trace is monotone. So before I sum this inequalities up, I will apply the function f of this minus f of this to both sides. So let's do this. Let f be any increasing function, actually non-decreasing, but non-decreasing. Function. Then we have this implication x less than y implies trace f of x is less than, it's a number, so it's a usual less than, trace f of y. Yeah, now the proof is simple. The trace of f of x is just, well, let's recall, what's f of x? F of x is a matrix with the same eigenvalues as x, eigenvectors as x, sorry, and whose eigenvalues are f of lambda I of x. That's how you make f of x. You apply f to the eigenvalues, and then we sum them up. That's a trace of that. And the trace of f of y is this for y. Yeah, and they do compare. Of course, this is less than or equal to this y by this proposition. And the monotonicity of f. Lambda I of x is less than lambda y of y. Therefore, f of lambda I is less than f of lambda I, and therefore the sum is less than the sum. That's it. So that was our proof. Proof of this. Good. Any questions? Far so good. All right. Eigenvalues are individually monotone. Perfect. Trace is traces is monotone function. Perfect. But then by looking at this, we can ask a question. Well, hold on. What if we just remove the trace here? Will it be true? So question. Does the stronger result hold? Is it true that x less than y implies f of x less than f of y for any, let's say, increasing function or non-decreasing function? This will be a stronger result, because then if that is true, then we can just take the trace on both sides and get the corollary. It's a beautiful question. So does a usual, it's a definition of monotonicity for numbers, right? F is called increasing function if x less than y implies f of x less than f of y. That's a definition. So it should hold for matrices if the world was ideal. And unfortunately, it doesn't. It's true for commuting x and y, but it's not true. So as usual, it is true for commuting matrices x and y. Again, do it yourself. It's very easy based on the fact that they are simultaneously diagonalizable, which means that their spectral decompositions are the same eigenvectors, but not in general. So generally, it is true for some functions f, and we call this functions matrix monotone functions. But not all metrics, but not all functions f. Not for all f. And this is an example in the homework. Actually, the square is not matrix monotone, unfortunately. Yeah, this is a little painful because monotonicity is such a nice thing, and it doesn't hold for matrices, but it does hold for a big class of functions, and we will, because I know how the course will progress, we'll prove it for two functions, namely for 1 over x inverse and for log of x. These two are matrix monotone. For these two matrices, this holds, and we will prove that, and then we'll need these two functions later. This is our plan for now, is to identify two matrix monotone functions. Namely 1 over x and log x. And it is actually not trivial. Any questions? Okay, let's do it. First proposition, the function from x to 1 over x is matrix monotone. Actually, let's do it, f of x equals 1 over x is matrix monotone. What does it mean? Again, it means that if x is invertible and positive, so it's positive semi-definite x and y is larger, then y is invertible and the inverse of x is greater than inverse of y, is greater than 0. It's not quite trivial, surprisingly. Okay, let's do it. Well, first of all, invertibility is not so difficult. If x is invertible, that means that all eigenvalues of x are positive, and positive semi-definite. All eigenvalues are positive, and that means that well, we have this monotonicity of eigenvalues, right? So this is greater than 0 for y as well. So this holds by eigenvalue monotonicity. And since all eigenvalues of y are greater than 0, this means that y is invertible. So we're done. Done with the invertibility. Second thing, let's prove the conclusion in the simple case where y is identity. Special case. First, we'll prove it in the special case, just an easier statement where y is identity. So we would like to show that if, let's call x something else, if, let's say, matrix B is between 0 and 1, then the inverse is greater than the inverse of identity, which is identity. Okay, so that's what we would like to show. I just rewrote this conclusion that for y equals identity, and x, I just changed the name to B for simplicity. Okay, now this one is really easy. Why? Well, because that thing means that, well, sorry, it's easy because they commute now. Because B and identity commute. Identity commutes with any matrix. And since they commute, then all the results for commuting matrices are almost trivial. This means that all eigenvalues of B are greater than the eigenvalues of 0, which is 0. And also, all eigenvalues of B are smaller than the eigenvalues of identity, which are 1. And of course, it follows then if I just revert this for numbers, it will be true. 1 over lambda I of B is greater than 1 for all I. And 1 over lambda I is the eigenvalues of B inverse. So this is true. For the identity matrix, perfect. And now in the general case. Okay, general case. So we assume that X and Y are comparable like this. And I would like to create identity on the right side and recycle part 1. So I will. Okay, you're okay with still with me, right? Everything is good. I don't want to lose you in this argument. It's just 2 lines more. So assume this is true. What I would like to do, I would like to make Y an identity and then recycle this argument. So how do I make Y an identity? I multiply by Y inverse, right? Only I have to be careful. I can't, if I multiply by Y inverse, something terrible may happen here. We already decided multiplication will make it a non-symmetric matrix, non-positive. So don't do that, right? Don't try this at home. So what is the proper way of multiplication? The proper way to multiply is to multiply on both sides. Then we're okay. Therefore, in order to make the identity here, I need to multiply on both sides by what? By Y to the minus 1/2 and Y to the minus 1/2 on both sides. Let's do it. So we multiply, we get 0 less than Y to the minus 1/2 X, Y to the minus 1/2 less than, and the right-hand side will be identity. Y to the minus 1/2 times Y to the minus 1/2. That's identity. Good. All right. Okay, now we can use part 2 for use part 2 to invert that. So we invert this, we get inverse of this matrix is greater than identity. I literally applied this right here. Perfect. And what is the inverse of this matrix? That's Y to the 1/2 X to the minus 1, Y to the 1/2. That's how you take the inverse. Greater than identity. Okay. Okay, so far so good. So what I need to come to this. So what do I do now? What's the last step? This is my goal. How do I get this from this?
Multiplied by 1/1/2 or y/1/2 twice.
Exactly. Twice on both sides, exactly.
Yes,
Just
on
do
both sides, and it's
exactly, Katrina. Thank you so much. So that's exactly what we do. We can do the same thing again. So we multiply again on each side, on the right and on the left, by y to the -1/2, and we're done. We get x to the -1 on one side and y to the -1 on the other. That's it. QED. Okay, good. It was easy, but not exactly trivial. Even the almost very simple fact that 1/x is matrix monotone. And the next and last result is that the logarithm is matrix monotone. Let's say natural logarithm, doesn't matter. And that means that if x is invertible and 0 is less than x less than y, then log x is less than log y. Okay, let's do it. All right. We're going to use the fact that 1/x is monotone to prove that log x is one monotone. So we're going to link log to 1/x. How is log of x? What is the link between log of 1/x and 1/x? What rings in your mind when you look at these two functions, logarithm and 1/x? How do they? Taylor, yes, Taylor.
derivative, maybe.
Derivative,
Derivative.
Exactly. Derivative. So that's what rings the bell. The derivative of log x is 1/x, and the integral of 1/x is log x. Yeah, this is how they're linked. Only and we would like to have that. We would like to use that link. So 0, I don't know, something from 1 to x maybe, 1/x, 1/t dt, I think. Only I can't really do that because if I start to work with matrices, I can't integrate over how to integrate over with the limit that is a matrix. X will be a matrix very soon, right? So that's not possible. So we will use another formula, not this one, but a very simple version of the same idea, the very simple version of this formula, and it is this one: log x equals integral from 0 to x 1/1 plus t minus 1/x plus t dt. Just check this formula. This is a simple integral. Resist the temptation to bring this into the common denominator. Just take the limits. Take a definite integral with the variable limit and send it to infinity. You'll see it's a simple thing, and that holds for any positive x, any non-negative even, I think. Yeah, positive x. Okay, check it. The advantage of this formula over the old one is that I'm really integrating to infinity. We would have very hard time integrating to a matrix here. All right, let's put it in a matrix form. This will be fun. The matrix form of this integral identity. Let's just imagine what it should be. Logarithm of a matrix now, x equals integral of something dt. Okay. Now let's move to the matrix world. How do I change this? What do you think this should be? 1 over 1 plus t. That's a number, so it should stay the same, right? But the result should be a metric. So what should I put here? How do I change it?
Multiply by identity matrix.
Identity, exactly. Trivially, right? I want this to be a matrix, and it doesn't even depend on x, so it should be identity multiplied by identity minus. And then how does this become a matrix? So imagine now x is a matrix. What is this then? 1 divided by x plus t. So
Maybe it's inverse to matrix X plus identity multiplied by T.
by t, exactly. Yeah, exactly. So we take matrix X here. Then we add t to it, which in the matrix form, we should be adding the t times identity. And then we're taking the inverse, which is 1 divided by, like this. And it should be dt. Yeah, so if everything was okay, it should be the true form. Let's check it. But is it clear that this should be, like, if everything is okay, it should be the formula? What else can it be? Yeah. Okay, let's check it. That this is indeed the correct formula. How do we check it? Well, we'll need to check the eigenvalues. So log, let's say eigenvalues, log lambda I, where lambda I is an eigenvalue of x. We first write this formula, let's say star, double star. So by the star formula, we just write it 1 plus t minus 1 lambda I plus t dt. And then log x is, so x is the sum of lambda I, ui transpose, it's a spectral decomposition. And then we just do the spectral decomposition here of log. So that will be log of lambda I, ui transpose. And then we expand each log as an integral. So it will be sum of integral, and they commute. This is Fubini theorem from integral to infinity. Sum minus 1 over lambda I plus t ui transpose dt. So this is Fubini, when I just change the order of the sum and integration. And then it's obvious what we should do, right? There is 2 parts, so we break it down into 2 sums. One sum is 1 over 1 plus t is a common factor. So I get ui transpose, and the other sum stays the same. ui transpose dt. Okay, so I did the obvious thing. I just expanded the logarithm into the integral and then did Fubini on it. And this is, what is this? Identity. Agreed? UI is an orthogonal basis of identity. And this is, by our definition of matrix functions of matrices, that's x plus ti inverse. So we're done. We proved this matrix version of our integral. Just checked that the scalar identity upgrades to matrix identity automatically. Perfect. And then everything is very clear. So how do we prove that log is matrix monotone? Well, if x is less than y, then okay, so we'll be using this formula. That one. Then x plus ti inverse. Okay, let me do it carefully. X plus ti is less than y plus ti. then by the previous proposition, because the inverse is monotone, we can invert that. Greater than y plus ti inverse. And that means that log, yeah, and I need to take the minus sign, sorry. Because that guy comes with a minus sign, so let me do this. Flip the sign again, like this. Sorry about that. Less than minus this. And that's it. So as soon as we have this comparison, I just put it in this matrix form and integrate, and the sum and integral is okay. So log x is less than log y. Just put that in the integral. Done. QED, log is matrix monotone. Any questions about this one?
Can you explain a bit how integral monotonicity translate to our new order relation? It's like last step when we deduced that our inverse matrices are based at well, one less than another, and then log x less than log y. It's evidently.
I see. So explain from here to here, this step.
Yes.
Yeah, sure. Yeah. I was going over this too fast. So, okay, let's do this step. So we have that term less than this term. Very good. We substitute this into here. So we write log x, we write log y. Then let me actually move it a little bit out. Okay, sorry about the mess. So we write the same for log y. So this is less than minus y plus ti identity dt. And then we integrate that. So we implicitly use the following fact that if we have two functions, matrix functions like a of t and b of t, and if this is true for any t, then the integral of a of t is less than the integral of b of t, right? This is what was hidden in this argument. You agree? So this is one function, and this is the other function. And now exactly. So the step that we did not explain is how do we actually integrate things. So that I should have said that. You're right. So that is true. Let's just think. Is that true? So what is the integral, first of all? How do you define even the integral? Let's look for the first principles. How do we define the integral? It's a limit of what?
Integral sums.
Exactly, Tatiana. It's an integral of sums. It's called Riemann sums. So the first step would be to prove it for sums, right? If you have matrices like this, then the sum of these matrices is less than the sum of bk. But that should be clear, right? If you sum two matrices, if a1 is less than b1, a2 is less than b2, then a1 plus a2 is less than b1 plus b2. That is actually true. You can check it quickly from the definition. And then you take the limit. Then you have to check. You're right. It'll be boring to do that. So if xk of t is okay, I'll not write it clearly, but you need to check that the limit is monotone too, which is true. So yeah, but I agree that step was hidden there. Any other questions? At this point, if I was here in class, I would say, oh my goodness, this is so hard. Like for any functions, 1 over x, really like simple. For log x, you have to do all this. Even for log x, come on, you have to come up with this identity. How do you do that? Would I have to, if I have another function, exponential, I don't know, sine function, whatever. Do I have to do all this again? I have to find some non-trivial representation of this function. Is there a general theory? Is there a general theory that I'll just get my favorite function and I check something and then say, okay, it's matrix monotone, it works. Instead of trying to do this by scratch, from the scratch every time. General theory of matrix monotone functions. There is a theory of general matrix monotone functions. It was developed by Loewner, and that's where we got the name of this order, Loewner order, in 1936. And this is a keyword, matrix monotone functions. If you Google up, you'll see a lot of modern expositions of this theory. It comes with characterizations of matrix monotone functions. So if we had that theory, we would immediately tell you, yeah, 1/x is matrix monotone, and log is matrix monotone, and some other, and square is not matrix monotone, for example. And just to give you a gist of this, in fact, this integral plays the key in that theory. Any function that can be expressed in kind of something like this integral is matrix monotone, and only such functions. So yeah, check it out in Google. I'll not spoil the pleasure of discovery. And yeah, so this area is well understood by now. And that's, I went well over time, I'm sorry. But next time we'll apply this theory. Any questions? Don't forget to come tomorrow. Tomorrow 6 p.m. right? The class is at 6 p.m. I'll stop recording now.